Welcome back, everyone! Across research labs and experimental platforms around the world, scientists are now developing machines that can flow, reconfigure, and adapt their shapes much like liquids. These liquid robots are not science fiction anymore. Using soft materials such as magnetic droplets, gallium-based metals, or programmable gels, researchers have created robotic systems that are flexible, self-assembling, and capable of movement without rigid parts. The goal is to create intelligent tools that can squeeze through narrow spaces, self-heal after damage, and function in environments that are impossible for traditional robots to navigate. Liquid robots function by replacing rigid mechanical parts with materials that remain soft or fluid under normal conditions. These materials include metallic alloys like gallium that are liquid at room temperature, soft elastomers that can stretch and deform, and smart gels that respond to heat, light, or magnetism. To operate, these materials must be given form and direction using external control systems. These controls may include magnetic fields, electric currents, or temperature gradients that induce changes in shape, stiffness, or flow behavior. This fundamental shift allows movement and reconfiguration without motors or joints. Magnetically responsive liquid robots use tiny particles of magnetic material suspended within a soft or liquid matrix. When an external magnetic field is applied, these particles align, causing the robot to change shape or move in a specific direction. Researchers carefully design the pattern of magnetic responsiveness across the structure so that the robot can bend, twist, or elongate in controlled ways. The benefit of this method is that movement is wirelessly controlled, allowing the robot to pass through enclosed spaces or operate in sealed environments where direct mechanical control would be impossible. Some liquid robots are made from metals like gallium or eutectic alloys that melt just above room temperature. These robots are designed to melt and reassemble on demand. Engineers apply heat to liquefy the structure, enabling it to flow into new shapes or around obstacles. Once cooled, the material resolidifies into a functional form. This transformation can be repeated many times, offering a new kind of durability. Rather than breaking under stress, these robots can escape confinement, bypass damage, and then reconstitute to resume operation. This is radically different from traditional mechanical systems. Programmable gels offer another avenue for building liquid robots. These soft materials swell or contract in response to stimuli such as light, electricity, or chemical exposure. When designed properly, a robotic system built from such gels can deform in predefined patterns. For example, exposing a section of the gel to ultraviolet light may cause that part to shrink, while another part remains expanded. By sequencing these reactions in time, the robot appears to move or fold itself. These materials are being studied for medical use, especially in soft internal navigation tools. Actuation in liquid robots does not rely on motors. Instead, motion is often driven by field gradients. In magnetic systems, engineers change the intensity or orientation of a magnetic field to guide the robot forward or rotate it. In electric field systems, electrostatic forces cause attraction or repulsion between charged sections of the robot. In temperature-controlled robots, heat is applied unevenly to drive fluid flow. These methods require precise timing and calibration, but enable wireless motion and extreme miniaturization. Control algorithms must coordinate these field changes to create continuous movement. Sensing in liquid robots is also different from traditional designs. Instead of rigid sensors attached to joints, the robots use distributed sensing built into the material. This may include embedded particles that change resistance, color, or magnetic properties depending on stress, temperature, or chemical exposure. The soft body itself becomes the sensor, providing continuous feedback about shape, contact, or damage. This information is interpreted by external computers or by onboard soft circuits that guide behavior. With this kind of integration, the robot can adapt its shape based on what it feels. Self-repair is a critical function of many liquid robotic systems. When damaged or split, certain materials can flow back together and reform their original structure. This may be a passive process, relying on surface tension and chemical attraction, or it may be guided by magnetic fields or heating elements. Researchers have demonstrated robots that can break apart, travel as separate pieces, and reassemble into a functional whole. This makes them ideal for use in hazardous or unpredictable environments where conventional machines would fail permanently when damaged. Powering liquid robots can be done in several ways depending on the application. Some receive energy wirelessly through inductive coils, similar to wireless charging pads. Others harvest energy from their environment using thermoelectric or piezoelectric materials. In laboratory settings, robots are often powered and controlled externally to simplify experimentation. However, engineers are exploring compact energy sources like microbatteries or chemical reactions to support autonomous function. As these systems improve, liquid robots will become more independent, able to move, sense and decide without tethered inputs or monitoring. Communication within or between liquid robots can be achieved by modulating the control signals or by using light and sound. For example, changing the frequency of a magnetic field may convey a specific instruction. Alternatively, robots may emit pulses of infrared light or ultrasonic sound to indicate status or request assistance from others. These signaling methods are essential when multiple liquid robots must work together to complete complex tasks. Engineers are also experimenting with chemical signaling inspired by biological organisms to create robotic swarms that coordinate like colonies of living cells or bacteria. In the future, liquid robots could become part of our own biological systems. Imagine a soft robotic system that can enter the body through a small incision or even be swallowed, then travel through the bloodstream or digestive tract to deliver drugs, repair tissues, or perform diagnostic scans. Once its task is complete, it could exit the body or dissolve harmlessly. These systems might be constructed from materials that respond to body heat, pH levels, or cellular signals, allowing them to operate with unprecedented precision and minimal external control. This would transform surgery, medicine, and diagnostics forever. Looking further ahead, liquid robots may be deployed in deep space missions where adaptability and resilience are essential. These robots could reshape themselves to squeeze through narrow crevices, repair equipment on alien terrain, or build shelters by flowing into molds and hardening into solid structures. Controlled remotely or by onboard intelligence, they could function independently for years in extreme conditions without human intervention. Unlike traditional machines, these robots could split into parts, perform multiple tasks, and rejoin for more complex functions. The potential for autonomous shape-shifting tools in space exploration is virtually limitless. While the field of liquid robotics is still in its early stages, the progress is already impressive. Applications range from non-invasive surgery and remote pipeline repair to planetary exploration and intelligent construction. These shape-shifting machines can operate in dynamic environments, recover from damage, and perform tasks that rigid robots cannot handle. Once engineers achieve full control over their movement, stability, and response to external stimuli, we could see these robots take on real missions in the field. Thank you very much for watching. Please like and subscribe.